Okay, so back to Zimbabwe. A lot of you are familiar with the Great Dyke, but we do have lots of other intrusions in Zimbabwe. The focus of today's presentation is what is called the Zvishavane Ultramafic Complex. It used to be called the Zvishavane Ultramafic Complex, and it hosts the largest chrysotile asbestos deposits in Africa. So that's most of the Aki and Creighton in Zimbabwe. And we have lots of granite greenstone terrains, and associated with that, we have some parts that are composed of much older rocks, such as this area here called the Tokwe segment here. And then that's the Mashawa Igneous Complex. And today I'll be focusing in this area here. So South Central Zimbabwe is where the Zvishavane Ultramafic Complex is located. And it is thought to be, older than the Mashawa Igneous Complex that is dated at 2743 million years. So within the Tokwe segment, where is that? That's the Great Dyke here, and it strikes slightly north of northeast. And in this region here, Gori is over there, and that is where Shurugu is. We have this area here that's called the Tokwe segment, and it extends a little bit further north to form what is now being called the Sebakwe Proto-Creighton. And that is where some of the oldest rocks on the Creighton have been reported from. So this is the famous Mberengwa Greenstone Belt. And you can see this is the region where we find the Zvishavane Ultramafic Complex in here. I'll get close to that one. So if you see over here, if we zoom in, that is the Zvishavane Ultramafic Complex, and this is where the Great Dyke is offset, and the town of Mberengwa is here, after which that classic greenstone belt is located. And here, this is a geologic map of the area. So that's the Mberengwa greenstone belt here. And just next to that is the Zvishavane Ultramafic Complex. It was intruded into the Zvishavane Gneiss Complex. The age is 3495. So that's some of the oldest gneisses in Zimbabwe. But we have some younger gneisses, part of this Zvishavane and Chingezi, and their ages range from 2818 to about 2684. So if this was emplaced in the Zvishavane Gneiss Complex, the age must be younger than the youngest one, which is 3088, but it must be older than these youngest ones of these intrusive granites. So if we go to this region here, we can see that we have lots of rocks that are similar in composition and in fact to be similar in age to this Zvishavane Ultramafic Complex, such as these ones here that you can see near the bottom of the Belingwe greenstone belt. So if we go to the next diagrams, before we get there, we just want to set the stage right why we are doing this study. Just to say, most of the studies have been in connection with the chrysotile asbestos, which is very important. Even though chrysotile asbestos is not being mined in lots of countries, you still have some, such as in Russia, Brazil, and in Zimbabwe. There's been no mining, but it started last year. So we just want to know something about the origin of this rock. There's been no mineral chemical studies that has been done in here. So this is a close-up. That's the geologic map of the area. And you can see that's the Zvishavane Ultramafic Complex. The cross-section here from drilling at the Shabani mine, you can see we have these various types of asbestos, and then the layered portion is composed of these ultramafic rocks. And then you also have some meta-gabbros and some meta-pyroxenites. And these ones here, that's part of the Berengwa Greenstone Belt. And that's the cross-section in this particular orientation. So as you approach the area, you are in the gneisses. So all this region here is in the gneisses that it tends to form low-lying areas. And if you get closer, you'll see that the Zvishavane Ultramafic Complex is more resistant to weathering. So it forms these hills here that you can see as you get closer. Okay. And here, this is just the Shabani mine. That's the largest chrysotile asbestos mine. And these are the tailings piles here. And that's part of that complex. And then what about the outcrop pattern from sampling? This is in some of the areas that mining has been going on, and these are the dumps here. That's part of where they've open pitted to mine the asbestos. So here, all these are serpentinites where the mining has been occurring. And then here's the trigonometrical beacon in one of the areas where we have some danites that have been metamorphosed. So the proper name, if you want, is metadanites. And then the other common rock type that you see are these metagabbros. And this is where the samples were obtained from, typical outcrop of these metagabbros. And then we studied these rocks under the microscope. And the type of minerals that you see under the microscope, as well as under the electron microprobe, you tend to see serpentine iron oxides, amphiboles, feldspars, clinopyroxenes, olivine, and I discovered this titanite, which might be very important to date this, but the sample that we shipped here, it's not enough to get an age date, so we have to try and get some more of those samples. So under the microscope, you can see the serpentinites, lots of these, veins that is altered the olivines. So it's dominated by serpentine and some iron oxides here. And then if you get to the metadanites, these are the only ones. You can see the relict cumulate texture. That's in plain polarized light, and that's in crossed polars. So most of the olivines have been altered to serpentine, and that's the same in this case. And then if we get to the metadanites, the metagabbros, you can see most of the feldspars have been altered to epidote. And then this is where you find titanite in here. And I'll show you some of those as well under the electron microprobe. However, we still have some feldspars, and most of these are, sodium-rich feldspars and the titanites. So more of the metagabbros here under plain polarized light. You can see the amphiboles and the plagioclases, and then this is under crossed polars, same view of plain polarized light and cross polarized light. And then we still have some clinopyroxenes, and here you see the typical 120 degree, 56 degree of your amphibole, very good cleavage. So lots of epidote from alteration of some of those feldspars and amphiboles. And then what we see under the electron microprobe. So you can see here, starting with the serpentinites, most of these you tend to see just veinlets, and the serpentinites here, and of course the iron oxides, you tend to see those everywhere. And then very little amphiboles. And then in the metadanites, some areas have been completely serpentinized, but some areas still retain what I interpret to be relict olivine crystals, but lots of serpentinization and those iron oxides. And then the metagabbros, the type of amphibole that you see in the metagabbros, that's the magnesium hornblende, and that's the plagioclase phosphorus from various types. And then that's the titanite here, and plagioclase. That's mostly what you get to see in there. And then I plotted the data from, you know, serpentine, all those phases, and then starting off with the serpentinites. The most common mineral is serpentine, and then what type of serpentine is it? If you plot it here, magnesium and iron, you can see that unlike the other serpentine, this one, it has much less MgO. So from my interpretations, because of the fluids that affected these ones, most of the magnesium has been carried away. That's why these ones are now enriched in silica compared to typical serpentinites. In this case, they are chrysotile and lizardite. Very few antigorized. And then the clinopyroxenes, I didn't see any orthopyroxenes, but the pyroxenes that I have here, augite and the diopside, it is very enriched in calcium, the one that is typical in metamorphosed rocks. And then the olivines, the relict olivines, very enriched in magnesium. And here, if we look at the amphiboles are the magnesium hornblende and the actinolite. So the other one is epidote, the type of epidote. If we plot our epidote composition on this chromium, aluminum, and iron 3, we can see that we have mostly the clinozoisite. And then the feldspars on this ternary feldspar diagram, we tend to see that most of those feldspars are enriched in the sodium component and not in the calcium component, yet these are ultramafic rocks. So just a little bit of some diagrams that compare what we have here to the Mashava complex, the other one that also has lots of chrysotile asbestos, and I did some work on there recently. So you can see the ones from the study area here, they tend to have more or less the same chemical composition, but the Zvishavane Ultramafic Complex has a little bit more of the serpentines enriched in silica compared to the Mashava igneous complex. And then if you do the same for the magnesium hornblende, that's more or less the same range that you see in here. And as far as the feldspars, the same type of scenario, although in the other complex, which doesn't have as much high-grade chrysotile asbestos as this one, some of the feldspars, you can see that they are still more enriched in the calcium rather than the sodium component. That's the same story with the epidotes. So if we can just sum up the data that we have so far, we can see that we have lizardite chrysotile being the type of serpentine that we have, and then the amphibole magnesium hornblende, actinolite. As far as the olivine is concerned, very enriched in magnesium. Phosphorite contents are in the 90s. Okay. And of course, because I have amphibole and plagioclase, I can use some geothermometers to be able to constrain the pressure and temperature path. So from a lot of analysis, these are the results that I got, the average pressure and temperature. So one thing that I thought when I got these results, I said, you know what, you tend to see lots of these PT diagrams, yet they are not really made use of as far as I'm concerned. So I try to, go through some processes to plot my data on this type of diagram, pressure here and temperature. And you can see what I have here is that this complex tends to be consistent with contact metamorphism. And then some samples, if you want, when we use the typical, prograde metamorphism, we are in the green schist amphibolite facies. So what I can conclude from here is that it was the intrusion of those younger granites that affected the Zvishavane Ultramafic Complex. And that's really not something new, but the data that I have presented here is just really pinpoints to the intrusion of the granites as being the culprits in the metamorphism that affected these complexes. And then I also used the data that I have to try and independently estimate the depth of metamorphism. So if you assume lithospheric conditions and you compute the results that you have to try and estimate the overburden above this intrusion, you can see that you are averaging, depth of about 2 kilometers, somewhere there. That is also consistent with the contact metamorphism. So part of the reasons why I also was interested in doing this work was to be able to say, why doesn't this intrusion have PGE mineralization? The inferred age of this intrusion, like I said, is between like 3088 to 2808 million years. If you want, that can be comparable to the stellar intrusion, Mani, Australia, same as Windimura. And there are lots of reasons, in addition to the ones that that we included in the abstract. Boudreau, for example, in 93, chlorine abundances. In this case, we don't really know, but maybe the chlorine abundances might point towards, PGEs in this body. And then Wolf Meyer has also suggested that, where you have these conduit systems entering into the magma chamber, that's where you are also likely to have PGEs being deposited. And in this case, it appears the only goal has just been chrysotile asbestos, and there hasn't been any exploration for PGEs. So if these are done and people can pinpoint the conduit system to that, it is quite possible that it might host some PGEs. Okay, and other.
Jeff, could you start wrapping it up?
Okay, sure. Sorry. Yeah, one other possibility, Levi, is that because of all this orbitization, we are likely to have and all these fluids, we may have gotten rid or remobilized all those PGEs. Okay, so I would say that's basically what I have. I'm sorry I've taken up a little bit more time, but it's just some work. And then, of course, just to sum it up, the outlook still staying close to here. We'll be looking to work on the Mimosa mine here for the next International Platinum Symposium. Thank you so much. I appreciate your time.